In this video, I want to focus very specifically on the audio information coming in. So in a prior video, I talked about the Pacinian sensors and how they're very well developed and designed for mechanical energy, vibrations coming in through the skin. And now I want to talk about some of the auditory system and some of the challenges that we have with vibration when it comes specifically to the skull. I mentioned in previous videos that as mechanical energy transmits out, so as I'm transmitting the vibration from this tuning fork out into the air, that when it reaches certain differing densities, like the wall behind me, that that when you're in a room you get different reflections, and your ears actually determine and understand the fact that this sound source, my talking, as it's bouncing off the different walls, it's reflecting and it's going to reach my ears at different rates in time. There's a processing involved in that. And when we're taking our vibrations from the tuning fork and we're not only reaching the skin, but if you're trying to do things inside of the skull, we have a very big challenge when it comes to mechanical energy, getting the vibrations through the skull, because they're such thick and differing layers. And what you're seeing in the picture on the screen is the different layers of the skull. So this will be the very top of your head. You see that there's the skin itself, the epidermis, the epidermal layer, and then the superficial layers, the same fascial layers that we deal with in other modes of physical understanding of the way that the body works. And then there may be a layer of muscle, and then we get up to the bone itself. The challenges with the bone, when mechanical vibration hits that bone, it's coming from a density of air, which is a much, much higher sound speed through air. And then it reaches that first layer of skin. And then if some of that information, that vibration, transfers to the skin and then the layer of muscle, again, different densities, but they're pretty close to each other, that first layer of skin is going to be enough to cause big time reverberation or reflection of that sound off the skin. So we already have a huge problem just on air to skin density differences, that sound has a tendency to bounce off of those layers, and skin is high enough of a density to cause a big problem. Then the fact that there's this very differing density between skin and bone. If we were to remove the skin and then we were just bouncing things off of bone, it would be probably just as severe and extreme as if you were trying to bounce vibration off of this wall behind me. It is that much of a difference. So that means we're going to lose a lot of our sound vibration that we intended to get through the skull in some cases, and it really depends on the intensity and the frequency itself, in whether that vibration is even going to make it through the skull. And it is highly unlikely that there's a usable amount of vibration that once you get through the skull, that you're able to actually transfer that vibration from layer to layer. And if you look at these layers, they are such differing densities that you're going to get sound caught within these layers. That's the way sound works. It could be caught, so the sound, if I was to hold a tuning fork just off the top of the skull, not touching the skull or depressing anything, I'm going to lose some due to reflection, some of that volume of sound bouncing off the skin itself. Then when it gets to the bone, some of it's going to bounce off of the transition, the edge of the bone, the very edge of the bone. Then some of it's going to make it through. And when it does make it through, the problem is it has another barrier on the other end of that skull bone. So what will tend to happen here is there will be a layer where the vibration actually gets caught within the layer of skull bone. because on the other side is another changing density. And sound would rather be reflected off of that. So you're going to end up creating a sound duct and a layer in there where that vibration, the vibration that does make it through the skull itself and in that bone, it will stay within that bone. A lot of it will stay within that bone. That's why you can feel the transfer of vibration from one end of the bone to another as you start to vibrate bone. That's because the vibration gets caught within the bone. And it doesn't necessarily make it through to the other side of where you're trying to go for, which is really the neurons and the firing of the neurons within the brain itself. Then the brain's ability to take care of fluid, there's a lot of spaces in there. Whether they're actually compacted with fluid, it really just depends on the state and condition of your brain itself. There's almost like extra spillways, because we know that we get fluid buildup within our skin, that the skin can expand to take more volume, but the brain cannot, and that's where we have big problems within the brain. It doesn't have the lymphatic system that the rest of your body has. It has its own drainage system and the ability to have spaces like the subdural space and the subarachnoid space. The ability for fluids to move into those spaces so that you're not continually swelling the volume of the soft matter of your brain. So even through those areas, those spaces and those sinuses, as soon as whatever makes it past the bone itself, you've already lost almost all of your strength. Even if you hold it, the tuning fork, the unweighted tuning fork, 3 to 5 inches off the skull, you're still not going to get enough through each one of those different density layers to get to where you need to. If you were to understand the plight of an ultrasound technician, which deals with higher frequency sound from an ultrasound paddle, they're sending vibrations through different layers of the body. And their main challenges their main challenges are, and really what ultrasound is doing is it's understanding and it's sending certain frequencies into the body that is dealing with what is the right frequency that will bounce off of one layer, because they're different densities. So in order to get through and see on other sides of bones become a big barrier for ultrasound technicians. And they find certain angles, certain windows that they can look through, and the way that they hold the ultrasound paddle is pretty important, because they have to get past the bone, because there's a blind area behind it, or change the frequencies and the way that the settings to get certain information back, because you're bouncing things off, and the reception of it bouncing back to the receiver. Excuse me. It's really a two-way communication. Sending it out, having it bounce off of something, and coming it back. What we're trying to do with a tuning fork is to send it through the skull, but we really can't do that, because by the time it gets through, it's already in an unusable strength. So the main avenue through the sensor to the brain is going to have to be through the auditory canal. So in this picture, I'm just showing you the fact that the entire brain is surrounded by this protective measure, and that even holding the tuning fork, you're going to bounce most of it off. Not only the skin, but the layers of bone, and what does get through the first layer of bone is most likely going to stay within the bone. And then, of course, you have another open area after that. So you can see how there's a huge challenge when it comes to mechanical vibration and the skull, and in training your brain neurons to fire at very specific rates. Best route in the head is through the ears, the auditory canal. Now the auditory sensory system, you can see here on this image that we have to also account for how the ear itself can get sounds into the ear canal, and the shape of your earlobe is actually specifically designed to take vibrations that come in from different angles and bounce them around your earlobe and get it basically focused, get that vibration focused to get it into the ear canal. So the shape of the earlobe and the fact that we have an earlobe is really designed as part of the sensory reception, the ability to tell a specific direction and to get as much information into the ear, even if it's at an odd angle. So that vibration is going to transfer to the ear canal, and then it comes upon the eardrum, a tympanic membrane, that's going to vibrate based off of the mechanical vibration. This is where the air molecules transfer that vibration to another form of vibration communication. So this is the actual receiver at this point, is the eardrum itself, moving that tympanic membrane, and then that vibration gets transferred by the series of what's called hammer and anvil, and past that stapes is going to be the a transfer of the vibration into the cochlea area, and it's basically just a way to transfer the same vibration from one to another, very much like the Pacinian corpuscles send the same exact vibration of the same exact frequencies. So does the eardrum, transferring it into the from the middle ear into the inner ear, which is the cochlea, where all the different hairs and the processing of frequencies are done within that cochlea. And then once it gets within the cochlea, then it's sent further on. There's a certain process of hairs, and how those hairs, where they're located, they can detect frequency. So this is really about the first part of frequency mapping for the brain to understand frequencies as they come in. The processing system of the ears is not only location, but it's time. And now if we can understand the word of time associated to the word frequency, frequency means how frequent in time did something get received. So if we go back to the earlier videos of understanding sound as a matter of time and timing and volume, our auditory processing system actually uses both of them. But as far as the main processing system, we get frequency information, which the cochlea is designed to map and understand. Okay, so this is a specific frequency. It has the ability of filtering out background noise to certain signals, and if it's loud enough to process and move the tympanic membrane, that's really a signal to noise filter. And then the signal processing within the cochlea allows those hairs to determine the frequency and map that frequency. Now, the auditory processing system is also a binaural processing system. So what you're seeing in the picture is showing you that there's auditory, primary auditory cortex, and there's multiple stages that goes from the inner ear, from the cochlea, through the cochlear nerve, and transfers that information from one location to another within your the central part of your brain, and then it brings it outwards into a cortex. So we hear in stereo. The word binaural is used most of the time in sound healing to show that there's a different frequency arriving in both ears, and then our brain can create a third frequency and process that as the interval between the two received frequencies between the ears. Binaural also has another understanding within the audio processing system, auditory processing system, which means where is something located in space. So if I consider the fact that I strike this tuning fork and I hold it in this exact location, it is now being received by both ears. And not only by both ears in a direct route, but it's also bouncing off of the walls behind me and beside me, and that information is received in the ear as well. Now the frequency and the travel time in the reflections and direct travel to both earlobes, the timing matters, and sometimes the amplitude of this source matters as well. And that really depends on the frequency itself. There's different frequency ranges that your brain processes and your auditory system processes. Things below like 60 hertz is considered a flutter, and things above that it's dealt with in a different way. When you get up into the thousands of frequencies, the audio processing uses a different way. And so when we're dealing with our tuning forks and we're holding that in a location out here in space, the brain really needs the ability to tell where in a horizontal arc or azimuthal that tuning fork sound is going to be picked up. And the reason I'm showing you and telling you this part has to do with the fact that the brain, the auditory cortex, processing cortex, has a mapping system for space and time, and the inner cochlea has the ability to map frequencies. So we're talking about a very complex system. The thing that's really good for you to know is that when this sound source hits this ear and it hits this ear, the amount of time delay between the two is going to determine how far away from it, how far and where along that azimuthal arc, that horizontal arc. The brain can actually account for that. It's very difficult to tell in a vertical format where a sound is, but I can tell across the horizon where exactly that tuning fork is reaching my ear just based off of the time difference that they arrive into both ears. Then what happens is both of those ears are going to take that same exact frequency, but the timing and the length of the route that it takes to get to each one of those stages gets processed in each stage. Then eventually there's a correcting or a processing to where the brain is actually able to say, well, if it came from this ear at this time and this ear at this time, they are the same exact source. And based off the time difference, where is that source across my horizontal field? And if I can see the field, so let's sample our visual sensory to back up what I know and map out where exactly it is along my audio processing. So if we can add another sensory like our visual field, now our vision seeing that object really helps with a secondary correlation. And by the way, everything that I just told you are things we use in sonar in underwater acoustics. The way that we process signal processing, the way that we have incoming signals coming into our sensor arrays, all that works almost exactly like it does in the brain. The processing information that comes in, the way that it's signal processed, timing-wise, it all works exactly the same. The amount of time that it takes to travel physically through the different axons in our neuron processing system as it hands off from one to another, it's the location of neurons within our brain that controls a lot to do with the spatial orientation of where things are in our external environment. So keep that in mind, that where there are the ability to control the timing of certain things within our brain and the firing of certain things, that sometimes it is the exact length of the physical route that it takes to get to a location that's going to mean something in the processing of certain things. And I think that's the last picture for this part. So just keep that in mind in your audio processing system. There's a lot more involved in it, and this is kind of just an introduction to show you that it's very difficult to get things from the outside to the inside of the skull. And our biggest bet and our biggest ability to get to a processing system designed for possibly in training certain time-based systems is through the auditory system, through the ears. And that is really considered a special sense. And we play this out, this understanding out throughout our different processes and protocols that we use for VCT.